The purpose of this video is to introduce spherical mirrors, curved mirrors. In our last video, we looked at flat plane mirrors. And now we're going to look at how changing the geometry of the mirror changes the reflection that you see. So curved mirrors really mess with our brain. So on the left, we have some curved mirrors, and we can see the top image. This man looks smaller in the mirror than he actually is. And then when the mirror is curved a different way, the man appears much larger, appears a little bit distorted, etc. Rear view or side view mirrors on your car, they are curved so that you can see more of what's behind you, but that distorts image sizes and distances, which is why they have the warning that the objects in the mirror are actually closer than they appear, right? So curved mirrors are helpful, they are useful, but also they can really mess with our sense of perception. So let's talk about why this happens. Why do we see these wacky reflections when we curve the mirror? Here's some more curved mirrors messing with our brains. First, on the left, we have an image for the candle, which is inverted. It's actually upside down in that mirror. Next, we have a candle image, which is magnified and much larger. And then here we have a reduced image on the right. The middle and right images, the reflection is right side up. Whereas in this left image, it's upside down, right? So weird things are happening with the reflection of this candle. What's going on? What is the physics behind what's happening? More images here. We can see the same thing. Reduced image, magnified image, really magnified image, really magnified image. Some of these are inverted upside down. Some of these are right side up. So let's talk about the geometry behind what's happening. This is going to be a short introduction to the geometry, and then we'll hit the details in the next video. So here we have a curved mirror. This black line represents a mirror. It is a curved mirror. In fact, this is a cross-section of a spherical mirror. So it's a spherical geometry that we're looking at. So you can imagine that the sphere that this thing is made up of, and we just cut out one piece of the mirror. So it's a spherical mirror. We're not looking at the whole sphere. We've cut out a chunk. Let's get rid of the non-existent part of the sphere now. Well, actually, first let's show the center. That would be the center of your sphere. All right, we don't need that. Now, this is a floodlight. So it's a light that we can turn on. And all of the rays that are incident on this spherical mirror, meaning all of the rays that actually hit the mirror, are going to be coming in parallel. So here's one of those light rays coming in parallel. And if we draw a line from the center of our sphere to the sphere itself, one geometry fact about spheres is that this radial line is normal to the surface at this point. So geometry tells us that the line through the center of the circle is going to be normal to the surface of our sphere. And so if that's our angle of incidence, the angle of reflection must be equal to the angle of incidence. That's still true. It's just that there are different normals depending on where we hit. So that's our law of reflection, right? Angle of incidence equals the angle of reflection. Now let's look at this purple ray down here. It's coming in parallel too. And same idea. If we run a radial line through the center of the circle, that's going to give us our normal because it's a sphere. So it'll reflect off in such a way that the angle of incidence is equal to the angle of reflection. When that happens, the purple ray meets the red ray there. Now let's add in a few more representative rays. The yellow, green, and blue, they're all going to hit our spherical mirror. There's going to be more normals, more reflections, and it turns out that the geometry of a sphere is such that any parallel ray is going to meet at this point right here. We call that point the focal point of this spherical mirror, and we use the symbol capital F to label the focal point. Getting rid of a little bit of the background now, so we can talk about some more things. This green line that goes through both the center of our spherical mirror and the focal point, this is called the principal axis for this mirror. So some labels: capital C is the center of the circle, capital F is the focus, also known as the focal point. And then all light rays that are parallel to our principal axis will reflect back through the focal point F. All right, getting rid of a little bit more of that geometry now so we can look at just the details here. Capital R is is the radius of curvature of our spherical mirror. So the distance from the center of that sphere out, that's the radius, right? The radial distance. Lowercase f, that's going to be what we call the focal distance, which is the distance from the focal point capital F to the mirror. So this is the focal point lowercase f. It turns out, as a fun geometry fact, that the focal point for our sphere is half the radius. So whatever your radius is for your spherical mirror divided by 2, that will be the focal point. That will be the point where all rays parallel to the principal axis will converge to that focal point. So the capital letters up here, these are points in space, so that they can be located, but they can't be measured. And then the points down here, the capital R and the lowercase f, those are distances. We can grab ourselves a ruler, we can measure those in meters or centimeters. Fun fact about a lot of the spheres and then lenses stuff that we're doing next is you don't need to use SI units. Centimeters, inches, all of those are fine, so long as you're consistent in the units that you are using. So if SI units don't matter, just be consistent. All right, I've got an actual photograph of this now. Here are parallel light rays. I outlined it poorly in gray here, but here's a curved spherical mirror. It's just a cross section of a sphere. And these light rays reflect back, and they all converge here at the focal point. Kind of neat. Really hard to see in this image. The next image, I turned this mirror a little bit so that we could see the focal point a bit better. And so the parallel rays aren't coming in parallel to the principal axis anymore, but they still do meet at a focal point like that. So that's where we focus in our light rays. That's why it's called the focal point. All right, so that's our introduction to spherical mirrors. The geometry is such that we focus light rays that are parallel onto a focal point. Next video, we're going to look at drawing some ray diagrams and describing how this property of spherical mirrors having a focal point leads to some of the distorted images we saw at the beginning of this video.